So it's a little cold snap. I'm freezing. I know this class is always cold anyway, but 43 this morning. So yeah, we're going to talk about viscosity and flow today. And this is part of this whole section of the notes that's on non-equilibrium chemistry. So things where there's gradients. So we have these different gradients that we have set up. Like if there's a matter gradient, then you've heard of diffusion. Diffusion is that transport property where matter is moved from one spot to another, a high concentration to a low concentration. I think in the video I talk about a candle, and you light a candle, and there's the smell will diffuse through the room, and that's an easy way for you to detect diffusion. If you were to walk in a very still room close to that candle, you would smell more and more vanilla or whatever the candle is. Thermal conductivity. What were the three different ways to transmit heat or energy? Do you remember those in the thermal conductivity? There were three different ways: convection, conduction, radiation. Yeah, the radiative transfer of heat. And so you can tell if you're which one you're doing, especially radiative transfer of heat. Like if you're at a campfire and it's just really blazing and your face is really hot, if you just put your hand in front of your face immediately gets cool. That's the infrared light. So it's the radiation that's hitting your face that you're feeling on your skin. The warmth, just the warm air. But if you get above the campfire, it's incredibly warm because that's conduction. That's convection. So air currents is convection. So a convection oven, or now we call them air fryers. Okay, there's a heating element and a really high powered fan that just blows that hot air over your food. So they're not waiting for conduction to happen or radiative transfer. It's actually convection. Today we're talking about viscosity. I figure we cover the top three. We haven't really gotten into the ionic conductivity, but you'll get the idea because these transport phenomena have very similar equations. There's always some sort of gradient, and so in this case we have a gradient in momentum. Now it's pretty easy to identify or think about a gradient in terms of heat. You got a hot object, you got a colder object, right? And the gradient always goes towards the high end, right? So the gradient goes towards the hot, and the flow is in the opposite direction. So if this hand is hot, this hand is cold, the gradient goes uphill, the flow goes downhill. So in this case, it's a little strange. We have a gradient in momentum. So think about this. I've got up here, it's just like two plates, but you could spin this object to make a pipe out of it. And so think about the middle of the pipe, the liquid is flowing fast, or the gas. At the walls of the pipe, it's not flowing at all. Like there's some molecules sitting right next to the wall of the pipe and it's just not moving. So there's a huge gradient between the wall of the pipe, which is stationary, and the middle of the pipe. Or you could think of a river. On the riverbank, very little water is moving. In the middle of the river, that's where it's going fast. So that's a gradient. So if there's a gradient, there should be a flux that's going in opposite direction of the gradient. So what that's doing is if the momentum is the gradient, then the flux is called drag or viscosity. So there's a drag component that wants to slow things down. So here I've drawn that little boxes that we see in the other notes where the gradient is. You have this velocity gradient going up there, and then there's a flux in the opposite direction. And so it has the same kind of differential where we have this transport coefficient. It's the coefficient in front of that drag on the velocity with respect to the z direction. Okay, and so this transport coefficient is what we call the viscosity, and it's related to the average velocity, like for a gas, the gas velocity, the number density. This is the mean free path and the mass of the particle. So this is our term for viscosity. So we do some calculations. So we could calculate. Have done everything for argon in terms of all of the gas velocities and so on. So here it is for argon. What's the viscosity of argon at 1 atmosphere? So that's our root equation. Let me get my pen. We made some substitutions here. So we've substituted for this number density. We used the ideal gas law, and this mass here we put in the molar mass. And so for these substitutions, we got these different terms here. Actually, the 3 is already there. U of RT and then the molar mass in grams per mole. And so then we can, at 1 atmosphere and room temperature, we also need to substitute for this, this mean free path. That's where we end up with this collision diameter. And we calculated that in an earlier set of notes. And so this was sigma down here, the collision diameter for the argon atom. This is the molar mass in kilograms per mole. We've got the average velocity that we calculated for argon at an earlier set of notes. We have Avogadro's number to get rid of the per mole on the mass. And then we end up with our units. So there's our viscosity in kilograms per meter per second. And then this is, one poise. So Poiseuille is the person that measured a lot of this flow, and then we've given him the name of the unit. And so instead of the whole name Poiseuille, we call it poise. 0.1 kilogram per meter per second is that unit. And so we're going to have, one order of magnitude difference between this. And so that 10 to the minus 7 becomes a 10 to the minus 6. And so that becomes micro poise. So this is for argon, 58 micropoise. Not very viscous at all compared to liquids. Now, does that make sense? Yes, it does, because the gases are not interacting with each other nearly as much as liquids are. So if a gas molecule is going through a pipe, yeah, there's collisions with adjacent ones, but there's not as many collisions as if it's a liquid. So liquids are in intimate contact. So dragging a molecule through a liquid, you can really visualize the drag force. The molecules are touching each other essentially. But a gas, there's a lot more space between the particles. Now there's another term called kinematic viscosity, and that's where we take the viscosity and we divide it by the density. And so this would be given the unit Stokes. So 1 Stokes is a centimeter squared per second. Okay. Now, when I was looking up comparing Stokes to poise and so on, I Googled the viscosity. This was just me, relearning some of this material, and I looked up the viscosity of water, and it was 1 centipoise. And I looked up the viscosity in Stokes, and it was also 1 centistokes. And I thought, oh, that means that the Stokes and the poise are the same thing, but they're not. Now, why would they be this? Why would the number be the same when the units are not? And this is for water in particular. Exactly. So we're just dividing by 1 right here for water. But for any other substance, the viscosity in poise and the kinematic viscosity in centistokes will be different numbers because you've got a different density. But anyway, I'm just letting you know how I was fooled so that you don't get fooled by that. So how does viscosity restrict flow? Well, the velocity gradient assists fast flow. If you have a higher gradient, then you're going to have a higher current in the middle. So remember, the gradient is the slope of this line right here. If it's not very sloped at all, you've got a lot of restriction on that flow. But if you have a high gradient, then you can have really fast velocities in the middle and still be still at the walls. And so then it's the interlayer collision. So if you think about these as laminar flow or layered flow, this arrow is going to be interacting with this velocity arrow that's pulling it along. This is pushing it along, but then this one is dragging it back. And so it's that drag that's the viscosity. Now I do a lot with cleaning, and so viscosity is very important for my research. And so high viscosity means slow solvent speed close to the surface. And so if you've got a dirt particle on the surface and you're trying to get that particle to wash off and you've got a viscous fluid, it's very hard to get these layers that are close to the surface to move, even if you're spraying it on something. You can think about that if you were in your mind, instead of using water in a pressure washer, using oil, right? It would just be coming out and it would be hard to get that velocity at the surface because it's so thick and viscous. And it would protect the surface. And what you see is sort of a boundary layer develop. And so this boundary layer, there's minimal velocity in the boundary layer. And so you really can't get good contact with the surface if you've got a viscous liquid. What about a low viscosity liquid? High speed solvent flow closer to the surface. So I've just taken that picture, shrunk it down. Like if you have a less viscous surface or liquid, then notice how this gradient is steeper. It gets to the fastest velocity by going by only this distance here, versus here it takes that distance to get to that velocity. So this is a steeper velocity gradient. And if you have the same size particle, you got faster flow hitting that particle. Now, if we define that boundary layer as just these bottom two arrows where there's minimal velocity, now the particle actually sticks up above that boundary layer. And so you're actually able to dislodge it using a fluid like this. So low viscosity is better for removing particles and cleaning. I know that you guys aren't in the cleaning research group and probably aren't going into cleaning, but people know that chemists that get out of SAM know a little bit about cleaning. And there's a lot of jobs out there. Every factory and every product that you see in this room, the surface had to be prepped, which means it had to be cleaned before it's coated, before it's glued. These wooden tables, there has to be the dust and particles need to be removed from that wood before they glue the top on. All of these surfaces here had to be cleaned and all the particles removed before they're coated. So it's something that people will be looking to SAM to hire graduates that know something about cleaning. Now, temperature dependence. How does it depend upon, how does viscosity depend upon temperature? Well, the kinetic gas theory correctly predicts an increase in viscosity with temperature, even though it assumes hard spheres, okay? Now, interparticle attractions account also for an increase in viscosity above those ideals. So in this plot, the lines are just for hard sphere predictions, and then the actual data goes above it. So as you raise the temperature, it's actually more than what's predicted by the ideal kinetic gas theory. Now, it can be complicated depending on the molecules with the temperature dependence. So like in this case, since the liquids are dominated by intermolecular attractions, and we talked about those in the Hansen solubility parameter lab. So how did that lab go? Did you guys have some success with that? Yeah. What did y'all test? Yeah, so what kind of plastics? Saran wrap, okay. What kind of solvents interacted with saran wrap? Mm-hmm. Okay. Water did not beat up? Interesting. Did it ever just get discolored with any of the solvents? Okay. You guys? What'd y'all test? Plastic folder, okay. What kind of solvents interacted with that? You don't remember? Okay, yeah. But anyway, you understand those Hansen solubility parameters. What are the intermolecular forces that we use to categorize, like put the solvents in their spots? Yeah.
Can you go to the earlier slide?
Yeah. Yes. It seems counterintuitive because you would think the viscosity would decrease with temperature because the molecules are able to move faster, but because they're colliding with each other, there's more drag. Okay. 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 Yes. So let's look at that. There's also temperature in the um, yeah. So up here, there's temperature in the denominator, but there's also temperature in that the gas velocity equation too. And then there's temperatures in the calculation of that mean free path. And so the temperature dependence is tricky to tease out. So, and so when you go to liquids, then kind of all bets are off because it depends upon the liquid. So if you have what I would say a normal, a normal like this normal liquid, we see a drop in viscosity at high temperature. So you've got a low viscosity for benzene, low temperature, you raise the temperature and you get even lower viscosity. Then in this molecule, something that might have arms that stick out at high temperatures and like it draws up at low temperatures. So in this case, if you've got like a polymer or a larger molecule, when it spreads out at high temperature, it spreads out and then all of a sudden you have a high viscosity. So for liquids, it can be really tricky to determine what's going to happen with the viscosity based on temperature. But in general, for liquids, you see this drop, like if it's what I would call a normal liquid, you would see a drop in viscosity with the higher temperature. And so this kinematic viscosity, we'll talk a little bit more about it. The SI unit, of course, is meters squared per second. And that's, again, very similar to those diffusion type equations. If you'll notice those equations, it was, let's talk about diffusion because that's easy to think about. You have a square meter in the gradient. So you've got that gradient set up like this where the gradient goes uphill. Let's see if I can draw the little box that they drew. So that's the gradient. And the flux goes in the other direction. And you could pick like a square meter there in that box. And you say, how many particles go through that square area per second? So that makes sense. The units are like a diffusion unit. You've got a square centimeter per second. You're talking about particles diffusing through that square area per second. If it's a higher flux, you've got more particles going through per second. If it's a smaller flux, you have less. Well, this is a situation where you've got the instead of units of particles, you've got units of velocity or momentum going through that square area per second. So that's why this is called a diffusivity of momentum. Since it has that unit of, an area square, like a Stokes is a centimeter squared per second. It's a units of momentum going through that square area per second. And if there's more, there'd be more drag. If it's less, there'd be less drag. Then we get into measuring viscosity. And here's where I think this is probably the best equation in this whole thing because this is Poiseuille's law. And this is what we used with the viscosity lab today. And then we've got this equation where we've got viscosity. This is like the greatest equation. Look at all the things we have in here. We've got the radius of the tube, and we've used this for the Ostwald viscometer, but we've got the pressure difference. So this is the pressures at each end of the tube. You've got the length of the tube. got the radius of the tube right here, and the viscosity right here. And this is the flow rate, volume per time. Isn't that great? This is everything you need to know about flowing through a pipe. And so I have lots of questions about this on the homework because this is one of the most useful equations you'll ever get out of this course. You're running you've got a clog in your drain line or something. How much you've got a certain flow through a 5-inch line, and now the clog from grease and oil has reduced that diameter by half. What happens to the flow? So we'll do some of those calculations here in a second. Okay, let's do one of those now. So flow is proportional to radius to the 4th power. So let's just do that. Let's see if I don't know why I'm thinking of a sewer line, but let's just say a sewer line. Let's give it a diameter. Let's say it's a 10-inch sewer line. 10-inch sewer line can flow 1,000 gallons per minute. And you get a big old slug of fat and grease and oil because people put all that stuff down the drain and they really shouldn't because of this. Have you heard of fatbergs? Berg, B-U-R-G, fatberg. We'll Google it in a second. Yeah. So a fatberg is instead of an iceberg, it's a fatberg, like in the sewer treatment, like lines of a city. Okay. So what's the flow if fat blocks the line to 5 inches, right? So in any of these cases, whenever you have a proportionality, what do you guys want me to do? We got all of these variables. How long is the line? Well, I don't know, but has it changed? No. How much pressure are we dealing with? Well, we don't know that, but we just assume it hasn't changed. So all of these things would cancel if we put the proportionality of one on top of the other and did the twos and ones and twos. So we'll just call flow F, right? So we have F2 over F1 is equal to R2 to the 4th power over R1 to the 4th power. Is everybody cool with that? And we know all of these numbers except for one. So we have F2 is equal to F1 times R2 over R1 to the 4th power. Now we had 5 inches over 10 inches, so we can put that on here. The inches have canceled, and we got to the 4th power. So are y'all with me when I say 5 over 10 is the same as a half? Okay. And what is 2 to the 4th power? 2, yeah, 16. So it's 1,000 divided by 16. So 63, 62 and a half. So Pretty dramatic change. Going from 1,000 gallons per minute to 63, just by cutting it in half. So you still got, instead of a 5-inch pipe, you still got a 10-inch pipe, you got a 5-inch pipe. 5-inch pipe is still pretty big, but with the same pressure, same length, same viscosity, all you're going to be able to flow through that is 63 gallons per minute. Huge change. Okay, what percent change is that? So we'll take 63 minus 1,000 divided by 1,000. That's a 94% change. Huge drop. We cut the pipe in half, we cut the flow by 94%. Yeah. So the most sensitive thing in this equation is the diameter of the pipe. Now, think about that too. If you just go from a 5-inch pipe to a 10-inch pipe, you think, okay, that'll double the flow. No, okay, it went up by 16. So if I was getting, let's say 100, let's use the 1,000, right? So I had 1,000 gallons per minute because of high pressure going through a 5-inch pipe, and I wanted to double the flow, and I thought, well, I'll just double the diameter. So we go to a 10-inch pipe. Now I can put 16,000 gallons a minute through instead of just 1,000 gallons, because it's to the r to the fourth. Okay. So these are lots of questions I could ask you. I say, okay, what diameter would you need just to double it? So if you only wanted to double it, then you could solve for R. Okay. Or change the viscosity. If I had 1,000 gallons per minute with this viscosity, what would it take to cut it to 500? Well, viscosity is in the denominator, and it's just to the first power. So if I wanted to cut the flow in half, I could just double the viscosity, since it's just proportional to the first power. So if you double the viscosity, you cut the flow in half. If I measure the flow rate, then I could calculate the viscosity. So that's what we do for the Ostwald viscometer. It's the same equation, but it's rearranged a bit. And so we have this flow rate, we have the density of the liquid, the gravitational constant, the height of the liquid, and all that stuff. And so what we typically do is we'll bring the viscosity over on this side, we'll put the flow rate down here in the denominator, and then we'll take all of this stuff right here, which doesn't change if we use the same viscometer, the same piece of glassware. We still have the same diameter of the glass and all of that stuff. The only thing that changes is the density of the liquid. And so this stuff gets lumped into K. So there's our viscometer constant for that piece of glassware. So you'll measure your viscosity of water to get K, and then you'll use that K to measure the viscosity of like a soap solution or something else. So
why does the pipe, so like if you had a polar liquid, and the pipe is non-polar,
yes,
versus like a non-polar liquid, flow should be there.
it might if you had like an extremely narrow pipe, like where that molecular effect was significant. But once you get beyond the boundary layer, then it's just laminar flow. So that boundary layer is affected by the surface. So whatever kind of surface you have, that would set up that boundary layer. But after a few, I don't know what the number would be. After a few monolayers of liquid, then you lose the memory of what that surface is. That's the way I think of it. It's like, yeah, the molecules right next to the surface have really locked on. If it's a clean surface, you've got polar bonds of the water or whatever, they're attracted, and those water molecules don't really move. But then you get a few layers away from that surface, and now it's just water moving by water. Yeah. But if you had extremely narrow capillaries, like these microfluidic devices, where you're down to, I mean, I don't know that they're moving single molecules, but they're getting really, really narrow channels, and they can use, then they can use, charges, electrical fields, and so on to move liquids through these tiny channels. So there you are getting kind of what you're imagining, where the intermolecular attractions of the fluid are interacting with the surface of the pipe. Yeah. Does that make sense? Yeah. So even our most narrow capillaries that we can see with our eye are probably like 200 microns, which is, that's like a swimming pool size for the molecules. So they don't even know really what's going on at the surface. Yeah. Cool. So while I was at the trade show, the PMTS, let's see, just a second. Let me show you some pictures of that trade show.